Alright, so this video is going over how to go about drawing free body diagrams. So the first question is, what is a free body diagram? It is a visual representation of all of the forces that are going to be acting on an object. It's going to show both the magnitude, or how large the force is, as well as the direction of each force. Since the arrow, or the size of the arrow, represents the magnitude, so the longer the arrow, the bigger the force, and the direction of the arrow shows the direction of the force. Now, we are going to always have the arrow that goes to the right will be on the right side. The arrow that's going to be a leftward force will go on the left side. However, it's important to realize that that does not matter. I could have the arrow that's pointing to the right on the left side. We just pay attention to the direction the arrow is pointing. And then the object that we are talking about that has the forces acting on it, it's either drawn as a dot or a box. We're going to draw it as a box just for simplicity's sake. So before we can get into drawing all of these different types of diagrams, we have to know what the different types of forces are. The first two, we kind of put them in the same as applied force, although one is applied and the other is considered thrust. This is a force that's applied by an object or a person. So in this case, the person is physically pushing or pulling a table. The person is hitting a ball, so the ball is doing an applied force the bat is applying a force to the ball. But in the case of a situation where something is flying, or like a rocket, then instead of calling it applied force, we actually call it thrust. But it's kind of the same concept. The propeller spinning is what is applying a force to the air to get the helicopter to lift, or the gas that's being ignited in a rocket is going to be applying a force on the object, getting it to move forward. So if it's an applied force, we use the capital A. If it's in the case of a flying object, we use capital TH for thrust. The next force is friction force. Notice it is a lowercase f. This is to kind of help prevent confusion between force and friction. So whenever we do friction, it's always going to be a lowercase f. What's important to know about friction force is that it's always in the opposite direction of the motion of the object. So in this case, if the box is moving to the right, friction is going to go to the left. If the box is going to the left, friction is going to go to the right. Friction is only present when an object is sliding across the surface. If it is not across the surface, if it's moving across air, it is not considered friction. So it has to be an object must be sitting on an object on another surface and moving in order for friction to be present. The next main force is the one that we talked about when we talked about Newton's laws, which is gravity force, or what we are calling weight. It is a capital W. No matter where the object is, whether it's in the air, on a surface, moving to the left or to the right, weight always goes straight down, because that is the direction of gravity. Gravity is always pulling down towards the center of the earth. Therefore, weight will always go straight down. Don't forget, we do not want to confuse weight and mass. Weight is the force. Mass is how much material makes up that particular object. So weight and mass are different things. The next force is one that we probably have not heard of. It's what's called the normal force. It is the support force. It is what prevents objects from falling through solid surfaces. So what prevents you from falling through your chair? What prevents a person from falling through the floor? Normal force always counteracts weight. Okay? So if weight is always going down, then the normal force will, for our purposes, will always go straight up. We're not going to do any inclined objects. You'll get into that next year. But for our purposes, will always be on a flat surface. So normal force will always go straight up. Weight will always go straight down. Normal force, more often than not, is going to be equal to the weight. However, in the situation, if an object is moving up or down, then the normal force actually will be different than the weight. But if the object is moving left or right, normal force will be equal to the weight. One other thing about normal force only exists if the object is resting on a surface. So if a person is standing on the floor, then there is a normal force. If a person is falling through the air, there is no normal force. The next type of force is the tension force, which is a capital T. This is the force that's transmitted through a cable or a rope or a string or a wire. So in this situation, if you have tug of war, these two people, if we were to turn this into a free body diagram, because the person is holding onto a rope and is not pulling that person by the hand, it would be considered a tension force, not an applied force. If they were pulling on each other without the rope, it would be applied force. But because there is a rope in between them, it turns into tension force. Same thing if an object is hanging, then that would be considered a tension force rather than an applied force, because the object is attached to a wire or a cable, and so we switch that to tension force. Next force is air resistance or drag, capital D. This is very similar to friction in that it is the opposite of the direction the object is moving. It's kind of like friction of the air. That's why it's called air resistance. So friction is resistance across the surface. Drag is resistance through the air. So if an object is moving to the right, air resistance would go to the left. If an object is falling down, air resistance would go up. And again, we would call it drag. So let's get into drawing some of these free body diagrams and how we go about it. The first thing you do is you draw a box to represent the object. Then you determine what forces are going to be acting on the object, as well as the direction of those forces and the overall general magnitude. We'll get into using actual numbers when we get into analyzing free body diagrams. For now, we're just putting them in relation to one another. Finally, we're going to use arrows to represent each of those forces. Each arrow needs to be labeled with the appropriate abbreviation. So for example, if this is going to be weight, the downward force, then I would make sure to label that arrow with a W. And if my object was on a surface, then I would also have a normal force. If the applied force is pushing the object to the right, then my applied force would be to the right, which would mean that friction would go to the left, and I would label that with a lowercase f. And then lastly, you want to make sure that you use a relative size for each force. If my object is being moved and is accelerating to the right, so say for instance it's a car picking up speed, then I would want the arrow for my applied force to be larger than my friction force arrow. When you are drawing these by hand, make sure that they are drastically different so that they're not confused to be similar, and that way I won't confuse it and think that you meant for them to be the same. So let's do some practice. If we have an object at rest, sitting on a table, a book at rest on a table, the forces would include gravity force, or what we call weight, and the normal force. So I draw my box, I would label my weight, and then I would have my normal force arrow. Because it's at rest, that means that those forces are going to be balanced, so my two arrows are identical. If instead it was Spider-Man hanging from the ceiling, I would still have gravity force, but instead of normal force, because he's hanging from a web, then it would be tension force. But notice my diagram looks very similar. The only thing that changed is that my normal force changed to a tension force. And since he's just hanging, he's not moving, again, those two forces would be identical. Now let's talk about constant objects with constant motion. So if a person is pushing a crate across the floor at a constant speed, the forces will include gravity force. Weight is always present. No matter what, weight will always be in every single free body diagram. Since the crate is on the floor, I would have a normal force. There would be an applied force because it's being pushed, and there would be friction because it's sliding across the floor. So I have my weight and my normal force. They're identical because the box is not falling through the floor, so they have to be balanced. But now we have to think about my applied and my friction. So the applied is going to the right because it's being pushed to the right, and my friction is going to go to the left. I know that, but the fact that it's moving at a constant speed means I actually want my friction arrow to be identical in size to my applied arrow. Remember, a balanced force can mean an object is not moving, or it can mean an object is moving at a constant speed. Okay? Falling through the air. A skydiver falling downward and speeding up. So weight is going to be present, as will air resistance, because they're falling through the air. So I have my object. I'm going to draw in my weight. Because they're falling down and speeding up, that's going to mean that my drag is actually going to be a lot smaller than the weight. This is what signifies that the object is moving in a downward direction and speeding up. The fact that my weight arrow is bigger and my drag arrow is smaller. Objects that have changing velocity. So let's imagine this. A rightward moving car has locked wheels and is skidding to a stop. So we're going to have gravity force, normal force, and friction force. The fact that the wheels have locked, the wheels are what push the car forward. They would be the applied force that would be moving the car. Because the wheels are locked and are no longer moving, there is no applied force in this situation. So what we have, the car is slowing down. So it's moving to the right, but it's slowing down to a stop. So I'm going to have my object, weight and normal force. Again, they're identical because the car is not moving, it's not falling through the ground. But since there is no applied force, but the object is still technically moving to the right, I'm going to have a friction force to the left, and that is the final diagram. There is no applied force. Yes, the car is skidding to a stop, so technically it is still moving to the right, but we have no force aside from inertia that is moving it to the right, so there's not going to be any force on the right side of this diagram. All right, objects with changing velocity, an elevator attached to a cable being pulled upward and slowing down. It's not touching the sides of the elevator. I put that in there because we want to know that we are not going to take friction into consideration here. So we're going to have gravity force and tension force. What's important here, even though the picture has a person in the elevator, we are focusing on the elevator itself, not the person. So my object is going to have tension force going up because it's moving in an upward direction. However, it is slowing down. So even though the motion is upward, if I was to think about the unbalanced force, if my object is slowing down, it means that the downward force, the weight, is actually going to be stronger than the tension. So this is my free body diagram for an object that is moving upwards and slowing down. All right, go ahead, try out these practice ones on your own and see if you can figure out what these diagrams should look like.